In the early 19th century, chemist John Dalton formalized a model of matter that would dominate science for nearly 100 years. He proposed that all matter is composed of atoms, impenetrable, solid spheres that cannot be divided into anything smaller. Every chemical reaction, every thermodynamic equation, and every law of physics constructed during this era operated under the strict assumption that the atom was the ultimate indivisible unit of reality. But in 1897, a bizarre anomaly occurring inside a sealed glass vacuum tube proved that assumption entirely wrong. The physicist who cracked the atom open was J.J. Thomson, working out of the University of Cambridge. Thomson observed a new subatomic phenomenon and devised a method to mathematically weigh it. His measurements proved that the atom itself has an internal architecture. The ground zero for this discovery was the Cavendish Laboratory in 1897.
At the time, the physics community was fiercely debating the nature of cathode rays. One faction argued these mysterious beams were a form of electromagnetic wave, like light. The other argued they were a stream of physical, electrically charged particles. The device used to generate and observe these beams is called a cathode ray tube. It consists of a sealed glass chamber hooked up to a vacuum pump, which removes virtually all the air inside to prevent gas molecules from interfering with the mechanics of the beam. Inside the tube are two metal electrodes. When a high voltage is applied, a distinct glowing beam travels in a straight line from the negative cathode to the positive anode. To resolve the wave versus particle debate, Thomson needed to manipulate this glowing beam using invisible crossing force fields. Inside a working cathode ray tube, we can isolate the beam's physics. Thomson introduced an electric field by placing metal plates above and below the path, positive on top, negative on the bottom. The ray deflects aggressively upward. According to the fundamental laws of electrostatics, opposite charges attract. Therefore, the entities making up this beam must carry a negative electrical charge. Proving the beam had a negative charge was only the first step. To confirm these corpuscles were actual physical particles and not merely an electrical wave, Thomson had to calculate their physical mass. Scientists couldn't weigh an invisible entity directly. Thomson introduced a perpendicular magnetic field exerting a downward force. Adjusting them until the forces canceled and the beam straightened, he set the field equations equal, mathematically isolating the particle's physical properties. Thomson effectively constructed a mathematical scale using crossed invisible fields. He used this technique to derive a precise charge-to-mass ratio, mass divided by charge, for a particle no human eye could ever see. The value he calculated for this corpuscle's mass-to-charge ratio is approximately 1.76 times 10 to the 11th coulombs per kilogram. This chart compares the newly derived ratio to the hydrogen ion, the lightest known particle. The math dictates this new particle is roughly 2,000 times lighter than a single hydrogen atom. To verify that this result was not a localized fluke, Thomson repeated the experiment. He swapped out the cathode for different source metals and introduced different residual trace gases into the tube. Across every trial, the calculated mass-to-charge ratio remained perfectly constant, regardless of the elemental source material he used. These negatively charged corpuscles, now known as electrons, are not unique to one specific element. They are fundamental, universal subatomic fragments chipped off from all atoms. Proving the existence of a subatomic particle immediately created a severe theoretical crisis concerning the physical structure of matter. Macroscopic matter is known to be electrically neutral, yet Thomson just proved that it contains a swarm of universal, negatively charged electrons. By strict logical necessity, there must exist an equal quantity of positive charge somewhere within the atom to perfectly cancel out those negative electrons. However, in the late 1890s, physicists faced a total lack of empirical evidence. Absolutely no positively charged subatomic particle, like the proton, had been measured or observed in any vacuum tube experiment. Thomson had to deduce a radically new atomic structure. He needed a mathematical framework that accounted for tiny negative point charges existing inside a neutral hole, without knowing what the positive component actually looked like. In 1904, Thomson published a theoretical solution known as the corpuscular theory. Today, it is heavily mocked and commonly referred to as the Plum Pudding Model.
Thomson hypothesized that the positive charge is not an individual particle. Instead, he modeled it as a continuous, uniform, fluid-like sphere of electrification. The negatively charged electrons are embedded directly into this positive matrix, like plums in a pudding. This configuration was not a random guess. It was a rigorous mathematical model derived entirely from the principles of static equilibrium and the balancing of electrostatic forces. Thomson calculated that inside this positive sphere, the electrons would mutually repel each other while being simultaneously attracted to the center. To achieve equilibrium, they would arrange themselves into highly stable concentric rings. As a physical representation of reality, this specific model was incorrect. It would be rendered obsolete just 7 years later when Ernest Rutherford discovered the dense, localized atomic nucleus. But Thomson's true legacy is the methodology itself. His rigorous mathematical derivation of the electron proved that the atom is a dynamic, divisible system. He opened the subatomic frontier, and modern physics followed.